Hello, my name is Maria Robinson, and this is a pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. Collaborators and supervisors of this project are Isabella DeStefano, Timothy Brady, and Ed Vol. In virtually any task, we need to make choices between different alternatives, and for this reason there is great value in determining the type of quantitative model that best captures this decision process. In this talk, we focus on two prominent probabilistic models of choice, a model based on Thurston's law of comparative judgment, which is instantiated with contemporary signal detection models, and a model based on Luce's choice axiom, of which the well-known softmax model is a special case. The reason we focus on these two models is because they are extremely prominent across different research domains. Also, there's quite a bit of early work that looks at the relationship between these models. However, much of this work seems to have been forgotten in some research areas. And as an illustration of this point, we focus on some contemporary work in the visual memory domain. I'm going to start the talk by reviewing critical early work on the relationship between these two models. Then I'll discuss how a comparison of these models is relevant to contemporary work in visual memory. And finally, I'll describe a critical test that we use to discriminate between these two models in the visual memory domain and what we found. The signal detection and Luce model come from very different traditions. The signal detection model comes from the psychophysics tradition, and it provides a detailed mechanistic description of the discrimination process. In particular, this model postulates that each stimulus produces some effect on the latent decision axis. So for instance, in the memory domain, a familiar object like this backpack will produce a familiarity signal of some magnitude. From now on, I'm going to refer to these effects as utilities instead of familiarity signals to make it clear that the points we make apply to a wide range of tasks and domains. A critical aspect of signal detection theory is that it postulates a probability distribution over these utilities. The most common parametric assumption made with signal detection models is that utilities are normally distributed. And historically, this normality assumption is made primarily for convenience and is often treated as an auxiliary assumption that does not have a clear theoretical justification. However, some early work by Thomson and Singh provides one principled reason for using a normal distribution to model the distribution of utilities. These researchers noted that each time we observe a stimulus of some kind, it produces some sensory response. And through the lens of contemporary population coding neural models, we can think of these responses as distributed patterns of activation in populations of neurons. So imagine a stimulus produces a neural response profile of some kind, as shown by these color distributions, and that these neural responses are converted to utilities in some way. Thomson and Singh pointed out that if these sensory signals are pooled together by summation or averaging, then by central limit theorem, these utilities will be normally distributed. So this provides a principled theoretical justification for using a normal distribution in the signal detection model. Finally, I'll note that while utilities are random variables, according to standard signal detection models, the decision-making process is deterministic. So that once utilities are specified, choices are made deterministically by comparing the utility to some criterion or another utility. The Luce choice model comes from a decision theory tradition. Unlike the signal detection model, it is silent about the mechanisms of the discrimination process, postulates that utilities are fixed, and that decisions are probabilistic. The model is based on an axiom that imposes a set of plausible constraints and choice probabilities. And the most important constraint is referred to as independence from irrelevant alternatives. And it simply states that the probability of choosing one alternative over another should not change if we add or take away irrelevant alternatives. This constraint is shown formally here. So if we have a set of items R that are a subset of a larger set S, which is a subset of a larger set T, the probability of choosing the subset R from subset S should be the same as the probability of choosing R from S if the subset S is chosen from T. So in other words, introducing new alternatives or taking them away should not change the rank order of a set of alternatives. An important implication of this axiom is that there is a ratio scale over the set T given by function V. So here V captures the response strength associated with a given alternative. Now, for some historical reasons and mathematical convenience, it's common to assume that this function of response strength V is exponential. And in this case, this equation turns into a logistic or a softmax model. It's also a short summary of the history of these two models. And based on this review, it might seem that the two models are extremely different, but in fact they are close approximations to one another in some scenarios, so I'll talk about that next. So in a detection task, where people have to report on the presence or absence of a target stimulus, or to recognize a target stimulus, the Gaussian signal detection model and the Luce model are close approximations of one another. According to the signal detection model, in a detection task, people simply compare the value of utilities which have some probability distribution against a fixed threshold. So for instance, people correctly respond that a target is present when it is present if the utility drawn from signal distribution exceeds a criterion C. Again, here we assume that utilities have a normal distribution. Now with the Luce model, we're not dealing with random utilities, but response strings. So these probabilities can be calculated directly from the formula, where alpha is a parameter that captures the response strength potentiated by the target, and V is a bias parameter. The connection between these two models follows simply from the fact that the logistic distribution approximates the Gaussian distribution and vice versa. And these two plots simply show that these distributions are close approximations of each other, and also that with a simple transformation, parameters from these models are functionally proportional to one another. So again, in a detection task, these models are closely related. Next, I'll talk about forced choice tasks, where the relationship between these two models is not so straightforward. In a multiple alternative forced choice task, the observer has to choose one alternative out of a set of alternatives. So within the standard signal detection model, now the observer is computing the maximum of a set of random variables. And the reason the relationship between these two models breaks down, or becomes more complicated, is because it's known that for more than two alternatives, the distribution of maximums of normally distributed variables is not a normal distribution. Likewise, the distribution of maximums of logistically distributed variables is not logistic. So now the connection between the Gaussian signal detection and Luce model breaks down. But it turns out that we can establish an equivalence between the two models if we drop the normality assumption. In particular, Holman and Marley and others have shown that if utilities in the signal detection model have a gumball distribution, then the signal detection model is equivalent to the Luce model for any number of alternatives. Here we omit the proof, but we give you a partial result. So it's known that the difference between two random variables that have a gumball distribution is a logistic distribution. So for two alternatives, this result follows directly. For more alternatives, we provide an intuition. So consider the fact that the probability of a random variable being the maximum is like a joint distribution over the pairwise differences between that variable and the remaining alternatives. And as I noted, these pairwise differences also have a logistic distribution. So one critical takeaway is that we can recast the Luce model as a random utility model. In the current context, another critical result is that the Luce model is formally equivalent to a signal detection model with a gumball distribution. And the gumball distribution is an extreme value distribution, which is used to model the maximum of a set of random variables. So this has important implications for how we think people might process utilities, which I'll talk about next. So shown here are two figures, one of which I showed you before on the left. As mentioned earlier, the assumption is that each stimulus elicits a sensory response, and the Gaussian distribution implies that people pool these sensory signals via summation or averaging. However, the gumball distribution implies that people take the maximum of these sensory signals. Obviously, these parametric assumptions have different implications for how we think about processes across different domains. So next I'll talk about how we tested between these models. First I'll tell you the tests we used, and then I'll explain the motivation behind it. So we ran several visual working memory experiments where we varied the number of alternatives at memory tests. The reason we did this is because we wanted to see what model has parameters that are invariant across these changes in the number of alternatives. And so the reason we varied the number of alternatives is that we made the simple assumption that as we vary alternatives, people shouldn't change how they use sensory evidence to compute utilities. More generally, we assume that the better model should also be one that generalizes across these variations in task structure. And it turns out that there's an early experiment by Treisman and Faulkner that also used this test in an auditory forced choice task. I won't have time to talk about the experiments in detail, but I'll quickly summarize what they found. So these graphs show parameter estimates from the two models as a function of response alternatives given on the x-axis. And based on our logic and their logic, then this model should have constant parameters, so it should have a flat slope. On the left is shown a reanalysis of some data from Miller, and on the left panel is d prime, and on the right panel is beta. As you can see, the slopes for d prime are flat, whereas the slopes for beta are increasing, which provides provisional support for the signal detection model. However, these data are quite noisy. On the right is Treisman's replication, and as you can see, the results are somewhat ambiguous since the slopes change for both models. And we can't speculate too much on why that is, but an important methodological limitation is that people had to maintain all alternatives in working memory instead of being shown these alternatives at test. So it's possible that increasing the number of alternatives increased memory load and hurt performance. So we applied this critical test in the visual memory domain. One reason we did this is because, as I'll show you, this permits us to get around some of the methodological problems of the Treisman study. The second reason is that the memory domain is one in which the relationship between the signal detection and Luce model is not thought about much in contemporary modeling work. As a case in point, there are these two prominent models, the Target Confusability Competition, or TCC model, with Shergan, Wixon, and Brady, and the interference model with Oberauer and Lin. The details of these models are not important, but I'll just note that the TCC model uses a Gaussian signal detection model as a response function, whereas the interference model uses a Luce model as a response function. And neither paper provides a principal justification for using one response function over the other, and given the processing assumptions that the Luce model and the Gaussian signal detection model carry, it's important to have an empirical test to discriminate between these two models. So next I'll talk about our experiments. So we ran 3 experiments. In the first experiment we had people remember colors of a set of circles. So they were shown a memory array with 4 colored circles, and after a retention interval people were shown a discretized color wheel that had 2, 4, 8, or 16 colors, and they had to click on the color of the probed item. And the foils at test were chosen based on their psychophysical similarity to the target. In particular, we chose foils that were maximally different from the target color, so that we can make the simplifying assumption that the distribution of responses elicited by each item in the test array is are independent of one another. In another experiment, we had people remember instances of real-world objects. So here people were shown images of one real-world object one at a time. And after a retention interval, they were shown a set of 2, 4, or 8 objects, and instructed to click on the object that was shown in the sequence. Again, here we chose foils items that were from a different category and conceptually unrelated to all objects in the sequence. And we ran another version of the real-world object experiment that we made more difficult by increasing the number of objects in the sequence and decreasing encoding time. We ran this additional experiment to ensure that we could replicate our results across a range of task difficulties. So for simplicity, I'll refer to these as the easy and hard versions of the real-world object experiments. These are the experiments, and next I'll show you the results. So each column here will be the results from each of the 3 experiments. First, I'll show you % correct, and as you can see, it decreases in the expected way as the number of alternatives increases. Now here are the d prime estimates from the same experiments, and based on visual inspection, you can see they all appear to fall on a flat line. And here are the beta estimates from the Luce model. As you can see, they tend to diverge from the flat line. We can formally compare these 2 models by comparing their log likelihood since they have the same number of parameters, and as you can see here, this Gaussian signal detection model with a fixed d prime outperforms the Luce model with a fixed beta. And altogether, these results provide support for the Gaussian signal detection model. In this talk, we revisited the connection between the signal detection and Luce model. We reformulated the relationship between the 2 models in terms of comparison between 2 different parameterizations of the signal detection model, and discussed the different implications these distributions have for understanding processes. We discussed the critical test between these models in the visual working memory domain, and using this test we found consistent support for the Gaussian signal detection model. Our results are consistent with the view that people pool sensory evidence when computing utilities and visual working memory tasks, And more broadly, the results suggest that in the visual memory domain, the Gaussian signal detection model generalizes better across variations in task structures. Thank you.